Okay, great. Well, welcome to Windows Vista Exploitation Countermeasures. We've got Richard Johnson up here, and I'm supposed to tell you that Rich is awesome. So let's give a big round of applause for Rich.
Thank you. Glad everybody could make it this morning. I know last night was a lot of fun. Glad to be here too. All right, so today we're going to be talking about some new features in Windows Vista, focusing on kind of memory hardening and new technologies that are being added to prevent exploitation, or at least try to mitigate those risks. And it's my belief and generally observed that memory corruption vulnerability exposure can be mitigated through certain memory hardening practices. And as Microsoft is in a position where they have access to the source code and the internals, and they have the best perspective to consider what types of changes they can make that will, have the greatest effect to prevent general attacks and general methodologies for exploiting vulnerabilities. And so you'll see, over the last few years, each time a new major release of Windows comes out with the Service Pack 2 of XP, and when Windows 2003 Server came out, there's been increased technology added that's always been trying to, one-up whatever the latest attack is, the latest method of heap exploitation, etc. And so they're continuing that effort with Windows Vista, and they're trying to kind of, rather than just do one little piecemeal thing, that they're trying to take a better look at what can we do overall in the memory hardening aspect. Since now we're coming out with a new release, people are going to have to worry about porting their software and stuff anyway. We have a little bit more flexibility when it comes down to making major changes in the way things work. One of the features you may have heard about, I don't know how much exposure Vista's had externally so far, but you will hear about if you haven't yet, is there's privilege separation has been added. IE protected mode, it kind of runs in a low privilege by default, kind of sandbox. There's kernel patch protection, which is like patch guard, and code integrity, which kind of goes hand in hand with that to ensure that non-signed driver is not able to get loaded into the kernel. So you'll hear a lot about those in other talks. I talk about ASLR and changes to the Vista heap, and exactly what that means to people who are researching vulnerabilities, and what types of hurdles are going to be in the way in the future. But as I said, this is a thing where all operating system vendors should really be looking at. And so maybe it'll help if we start off by taking a look at what's out there right now, what operating systems are offering in general, and how important different vendors think memory hardening is, types of efforts they put forth so far. So Red Hat Linux, we'll just use as one example of Linux in general. They come with features such as compiling their executables so that sections are placed in a specific order that's not the default GCC compile section order. It's actually ordered so that when, if you were to overflow something like the BSS or the heap, static heap data, then you're not going to run right into other data that might be manipulated. You'll run into the or something like that, so you'll access violate. They also are able to randomize DLLs and have some limited randomization of their core executables. They do have some stack randomization. If you have a compiler like with ProPolice, then they're able to do some protection of the control flow data on the stack, as well as local variable protection by reordering them in order to prevent arrays, perhaps like a copy to a string on a stack into a structure or an array. Like they try to place those as close to that cookie on the stack. So they do a lot of things at compile time. They also, in the kernel side, support segment randomization for the stack and the heap. And so, in short, they've definitely observed that they can make some changes, and that if they apply these changes, then they're going to reduce the risk of attacks working one-off and reduce the reliability of exploits. So that's Red Hat. OpenBSD has their own implementations of the randomization and non-executable pages as well. They also do some local variable protection with their compilers. And section reordering and DLL randomization as well. OS X notably does not have most of these features. They do support a non-executable stack, and Windows has many of the same features. A couple of extras that are not supported by others. Most specifically, the heap protections that have been built into Windows haven't actually propagated to OSs yet. Nobody's really considering how to protect mallocs and stuff like that on Linux operating systems or BSD operating systems right now. So we'll go more into those later, but this is just kind of a little overview of where people are at, where vendors are at in their operating systems as far as how much effort they're putting into securing the memory features. So the past improvements to Windows memory hardening has been things like stat cookies that were added for compilers, that we saw in XPSP2 that try to protect the heap management data. Safe SEH was added, that's to protect the exception handling frames that are stored on the stack. And just recently, a couple months ago, Matt Miller and Ken Johnson were working on a vulnerability that had to do with the way that unhandled exception filter worked in Windows. And so that was just very recently patched and hardened. And so there's new memory checks around where your unhandled exception filters are pointing, and common misusage of that caused chaining to occur, and that led to basically dangling pointers out into the middle of memory. So basically, if you were able to heap spray, you could take control of that. So that's a new thing. If you haven't checked that out yet, it's a pretty interesting design problem. But that was addressed, I believe, in June. And then, of course, most recently, everybody's heard the most about the hardware dep and NX and all that good stuff, because the average Joe can understand that. So new in Windows Vista, we're going to be talking about ASLR, like I said, and the key points we're going to hit on are, where does the idea of ASLR come from? What kind of research has been done on it? What architectural considerations do we have to think about when we're considering it for the Windows operating system? And then kind of the internals, the technical details, how much randomization do we put in there? How does the system architecture maybe limit or help the way that they chose to do their ASLR? And then finally, we'll go through just several testing methodologies. When I sat down to analyze the effectiveness, and I was looking kind of from an attacker's perspective, these are kind of the things that I pick up on, or that people will have to kind of look towards in the future when they're targeting a box and that has these sorts of protections. And then after that, we'll talk about the heap, and we'll do a very, very brief lesson in just kind of what types of exploitations gone by so far, or what the common methods of heap exploitation are. And then we'll talk about improvements in the heap management. We'll get pretty low level and talk about the low fragmentation heap and the structures and the way that the new look-aside implementation, basically, low frag heap replaces the look-asides. And so we'll go pretty deep into detail there, because most people probably haven't been exposed to that. So ASLR, it's a technology that's basically designed to introduce randomization into the space, and effectively that creates a statistical problem when it comes down to trying to exploit a remote machine. And I say statistical problem because literally it's introducing a certain variable shift in where things are supposed to be. So your reliable one-off exploit is going to only be able to hit that 1 out of, in this case, 256 times. If it's on something like Linux and they have something like 12-bit randomization, well, it's going to hit 1 out of a number of times, given just that one shot. So it becomes a statistical problem. How often will your direct attack work, or what are you going to have to do when it doesn't? And effectively, they do this by allowing for the relocation of memory mappings, which means, when your heap gets allocated, when your heap segment gets allocated, or your stack segment gets allocated, or files get mapped into memory, that's where the memory manager is going to be shifting things around. So, the theory of ASLR is pretty basic. They say, and effectively, ASLR, especially in Windows case, is truly meant to defend against remote attacks. And so the theory is that exploitation relies on some sort of prior knowledge of the memory layout of the system that you're going to attack. And so if we can shift that around and you are not able to predict what that memory layout is going to be, well, then you're not going to be able to hit those function pointers that you want, or when you do your overwrite, you're not going to know what to overwrite it with, because the executables are going to be in different locations, et cetera. So the major published research on ASLR is the PAX documentation that you can see at the URL up here. They have pretty extensive docs on what their implementation was. They implemented software NX, which more or less emulates the non-executable bit for x86 architecture. And they also have a pretty optimized ASLR implementation for their memory randomizations. In fact, if you were to do a numbers comparison on PAX's ASLR entropy versus Windows ASLR entropy, you'd probably scratch your head and say, PAX has 12 bits on their stack and Windows has 4 bits or something. But the other reference that I have here is a paper that came out of Stanford called On the Effectiveness of Address Space Layout Randomization. And they took PAX head on, and they're like, well, let's do a case study of Apache running on a box with PAX and see what type of protection this entropy really gives us. Well, in the case of Linux, since you can brute force it pretty much as long as you want, and you have processes that fork and the address space is cloned that way, it actually turned out that they could very easily brute force PAX, given, I think it was like less than a day or something, it was a couple hours. And so with those two things in mind, like with kind of the model implementation of PAX and then the kind of counter study of the effectiveness of ASLR, Microsoft took those into account in the way that they were designing their implementation. So along with that, they also, of course, had to consider the operating system that they're building upon, the actual architectural considerations. So in Windows, most applications are threaded as opposed to forking. And this is important because for various reasons, actually. Brute forcing doesn't work the same because if you're going to crash one thread, well, you're probably going to crash the whole application. Or if you're going to spray the heap, well, you're going to affect the same memory that all the other threads are using. So it's a distinction between a forking-based sub-process model and a threaded-based model. In addition to that, the Vista memory management has a lot of restrictions on it, mostly for performance reasons and app compatibility. Things like a good example would be when you have an operating system that needs to be able to make sure that it can run in a very high performance environment where you have Oracle and maybe you have like databases that are like gigs of very large and stuff like that. You really have to concern things like fragmentation of your memory space and how large of an allocation can we make at one time. So all these things play in. And one other thing that's very different about Linux versus Windows is that Windows uses 64K boundaries for all of its image mappings, as opposed to Linux, which uses just page boundaries. And so that, out of a 32-bit address space, that's 16 bits gone right there. So you're thinking, okay, 16 bits gone, that gives me 16 bits left. What kind of, how can we take into account the fragmentation as well as we lose our lowest bit counts? So there's some interesting challenges when they have to consider how to do this for an operating system that's already deployed so heavily and already relied on in many places. Another property of Windows is that they use shared mappings of libraries across processes. So if I load kernel 32 in a process A, whenever I start process B, kernel 32 is going to be the same spot. And that doesn't apply just to certain libraries, that's actually applying to all of them. And that's to reduce the physical pages that you're actually occupying by each one of those mappings. So again, that's a little bit different from Linux. And then, of course, Windows now supports hardware NX, and pretty much every new processor you buy is going to support that too. So we can assume that ASLR and NX are going to go hand in hand. So a little more technical about the implementation of how they did the memory mapping. The image mapping is actually done based upon a single-time randomization. That's like on boot, it chooses one random offset into a certain segment to begin its DLL loading. And that's chosen with 8 bits of entropy, which is not much. That's 256.